This lecture is going to focus on generalized Hooke's law. We're going to take a look at it from two perspectives. One is from a material science perspective, and the other is from a tensor formulation. We're going to get the functional form of the strain energy density function. We're going to be able to derive our stress-strain relations from it. And we're going to reduce our generalized Hooke's law for the most general anisotropic material down to that for an isotropic material. We'll split this lecture up into two parts. The second part then will be on taking a look at the isotropic Hooke's law, and then the inversion of that in the relation to a more general, maybe a more familiar form of Hooke's law that you've probably seen. Alright, so in generalized Hooke's law, the basic idea is that stress is a linear function of strain. Well, why would we want to choose it to be a linear function? Well, there's a couple good reasons. Many of the materials that are important in engineering exhibit a linear range of stress-strain behavior. Like our steels, our aluminums, our metals, and many other useful materials. And if we're going to start with something, let's start with something that's relatively simple instead of going into the most complicated aspects of everything. Okay, so with that, we'll clean a new page here and we'll take a look at our material science type notation. Well, in the most general form of our 3D Hooke's law, each of our stress components can be written in terms of constants times each of our different strain components. And so with this material science notation, we're not taking advantage of the tensor type notation, but we can still write this in terms of a vector and matrix type format. On the left hand side, we have our vector of stresses, sigma x, sigma y, sigma z, the normal stresses, and the shear stresses tau xy, tau xz, and tau yz. I'm going to fill in one of these rows with different coefficients. I'll fix that one here in just a second. We have a big matrix, and then our strain components. And since we are not restricted to our tensors and our tensor notation, I'm going to use engineering shearing strains with our gamma notation for that. And so if I were to expand this out into the first set of equations that I would have here, my sigma x then would be equal to C11 epsilon x plus C12 epsilon y, and so forth. I'm going to go ahead and write the rest of these down. And we would get similar equations for the rest of these terms. Now, to save a little bit of time, I'm going to pause the video and fill out the rest of this matrix. And there we have all these terms in this matrix. Altogether, we have 36 terms in what's known as the stiffness matrix. We can even use our index notation to compact this a little bit. If we call our vector of stresses sigma I, we can say that it's equal to a Cij epsilon j, where we have the implied summation notation. And again, I do want to emphasize that this is material science notation, and what that means for us is that this is not a tensor. It does not behave in the way that tensors transform. But if we look at this, then we have 6 by 6, we have 36 entries in this particular matrix. We'll be able to show that we can reduce the number of unknown constants in this matrix down to 21. Alright, let's make a little bit of room and we'll show that. And the key to that is to go ahead and write down what our terms are for sigma x and sigma y, for example. So let me go ahead and write down this matrix line for sigma y. I'm going to try to be really careful and get all of these subscripts right, but occasionally I'll get talking or moving forward in my mind and write down some wrong subscripts, so keep a close eye on me. So we have these two lines that we have from that matrix, but the key here is to realize that these stresses we have assumed, based on our restrictions and assumptions, that they're derivable from a potential function based on partial derivatives of that potential function with respect to the strain terms. So sigma x would be the partial of u with respect to epsilon x, and sigma y would be the partial of u with respect to epsilon y. Now, if we were to take one more set of partial derivatives, that being the second partial derivative of u with respect to x and y, we need to be able to get the same thing from both equations. Well, let's look at this one. The partial derivative of sigma x with respect to epsilon y would be equal to C12, and the partial derivative of sigma y with respect to epsilon x is equal to C21. And since both of these are equal to the second partial of u with respect to epsilon x and epsilon y, then what we've done is we've shown that C12 is equal to C21. And in fact, we can do this for every term in that matrix. Let me call up that matrix again. Alright, and so C12 is equal to C21. Likewise, we can go through and show that each of these is a symmetric term. Alright, and so the unique components then of this matrix would be all the terms in this one, all the terms in the one right below that, and so forth. And so if we highlight each of these different rows that have these different terms in them, we can see the ones that I've highlighted have a decreasing number of unique terms because of the symmetry. We end up with 6 plus 5 plus 4 plus 3 plus 2 plus 1 terms. If we add all those up, we end up with 21 unique terms that describes the most general linear elastic anisotropic material, subject to our restrictions and our assumption that we have this derived. Our stresses can be derived from a strain energy density function that's going to be treated as a potential function. So 21 unique terms for the most general anisotropic material. That is linear elastic. '21 elastic constants. That's a whole lot of material testing in order to find these out. Now, a lot of nice practical materials don't have anywhere near 21 elastic constants. Most polycrystalline metals will be able to assume that they are isotropic on a macroscopic scale, and we can reduce this down eventually to 2 unique elastic constants. Some materials like carbon fiber composites may have a few more, but usually you don't see things that have as many as 21 elastic constants. If you get into certain crystal elasticity properties, then you may see more and more elastic constants to describe that type of material. Alright, well, let's take a look at finding our strain energy density function U. And that's going to be based on those first 2 lines that we have up there. The partial of U with respect to epsilon x is equal to sigma x, and likewise for the next line that we have there. We can integrate a system of equations, so let's take a few notes on that. Alright, so let's take a look at our first line. We have the partial of U with respect to epsilon x is equal to all the terms I have for sigma x. If I wanted to integrate that with respect to epsilon x, then I would get an expression for U that would look something like this. The first term would have a epsilon x squared over 2 in it, so I'm going to write this as 1/2 C11 epsilon x squared, and then all the other terms would be multiplied by epsilon x. And I'm just going to go ahead and do that. Again, keep an eye on my subscripts. And since this is epsilon x there, and since this is we're integrating a partial differential equation, we have to be careful. We could have other functions based on the other terms that we have in our expression. There could be other functions that just contain epsilon y's and epsilon x's and so forth. So I'm going to lump those all together, and I'm just going to write down plus other functions. And we could also have arbitrary constants. I'll list those separately. Now, the arbitrary constants really don't matter for us. When we go to find our stresses, we're taking partial derivatives, and those constants will go away. Now, the other thing to keep in mind is that when we do take the partial derivative of this U that we just found, we need to get, with respect to epsilon y, we need to get sigma y out of it. And we know what that looks like. It needs to look something like this. C21 epsilon x plus C22 epsilon y. And I'm not going to write down the rest of them, but I'll do the last one. C26 gamma yz. And so, in order to have that kind of a term, then U must have a term like 1/2 C22 epsilon y squared in it. and the terms that are first order will go away. So we can't have any term that looks just like a constant times epsilon x, because that has to disappear as well. When we take this entire system, these 6 equations, and integrate them, we basically end up with a form for our u that looks like this. It's going to look like 1/2 Cij epsilon I epsilon j. And since the Cij epsilon j term is equal to stress, it's going to look something like this. It can also be written as 1/2 sigma I epsilon I, where our epsilon I is our strain vector, and the sigma I is our stress vector. Go ahead and write these down. Here's our shearing stresses. And so with that, we're in a position to take a look at our reduction to isotropic materials. Now, we mentioned in the previous lecture that if we had a material that didn't depend on direction, then we can write the strain energy density function in terms of the principal strains. So U would be a function of just the principal strains, which I'm going to call here with our book's notation epsilon 1, epsilon 2, and epsilon 3. So it doesn't depend on our eigenvectors, doesn't depend on our 3 angles that we might use to describe our strain energy density function. So if we take a look at our notation that we had written down previously with our C's, then we can get a particular form for our function u. It's going to look like C11 epsilon 11 squared. And I'm going to go ahead and write down the rest of these. I may not say them all, but we'll have some terms that deal with C12 epsilon 1, epsilon 2. Basically, we're going to have all the different combinations of our principal strain terms. Effectively, we don't have any shearing strain contributions in this. We're in the principal strain directions. And that one should be an epsilon. Okay. Now, if we really are isotropic and it doesn't depend on direction, then we also have a free interchange among the principal stress components. So the one direction and the two directions should behave just the same. What does that mean then? All of these terms that have the normal principal strain squared are all going to be equal. So C11 is going to be equal to C22. It's going to be equal to C33. We also know from previous experience, looking at our terms, that C12 is equal to C21, C13 is equal to C31, and C32 is equal to C23. But because of this free interchange of the principal strain terms, then these are all also equal to one another. So the 2-1 and the 3-1 in the 2-3 are all going to be equal to each other. So what that means then is that we really have two unique constants to describe an isotropic material. Now I'm going to call these terms on the normal strain squareds, normal principal strain squareds. I'm going to call this elastic constant C1, and I'm going to call the ones that are on the cross terms, where we have 2 and 1 and 3 and 1 and all of that multiplied together, I'm going to call that term a constant C2. Let's make a little bit of room. Alright, so a material then that is isotropic can be described by two elastic constants. Well, if we call these elastic constants C1 and C2, we can reduce the form of our strain energy function and write it in terms of these two elastic constants. It's going to look something like, here's the half. We're going to have our first constant multiplied by each of the principal strains squared. I'm just going to group these all together. And then, so that we can write this with the half out front, we're going to have a plus 2 times our second constant C2 times these terms, epsilon 1, epsilon 2, and so forth, where we have the mixed principal strain terms. Now, our elastic constants, you may be familiar with Poisson's ratio, the elastic modulus, and the shear modulus. Turns out that the C1 and C2 can be written in terms of those values that we're more familiar with. But before we do that, we're going to have a little bit more work we're going to do to write this in a slightly more standard format. And in order to write this in a slightly more standard format, we're going to add and subtract like terms. So we're going to rewrite this. Here's the half. I'm going to take and split this up into 2 bits. I'm going to take my C2 and multiply it by this term. And I'm going to subtract that same term. I said that wrong. This second term here, I can rewrite that in two terms that look like this. The first one is C2 times epsilon 1 plus epsilon 2 plus epsilon 3 quantity squared, and the second term is going to be C2 times epsilon 1 squared plus epsilon 2 squared plus epsilon 3 squared. And then I have my first term that I'm just going to rewrite. Now, let's go ahead and I'm going to go ahead and show with algebra that these two terms are the same as this term right here. Right. We won't take a whole lot of time to do that, and I'm just going to pause the video and work out that algebra, but I think it's worth showing that that is the case if you don't see it right away. Alright, and here is the algebra worked out, and indeed, taking that term 2c2 times epsilon 1 epsilon 2 plus epsilon 2 epsilon 3 plus epsilon 3 epsilon 1 is equivalent to c2 times epsilon 1 plus epsilon 2 plus epsilon 3 quantity squared minus c2 epsilon 1 squared plus epsilon 2 squared plus epsilon 3 squared. So that does check out. And with that, we'll be able to write this function u by grouping terms that look like one of them is going to be a 1/2 c2 times the quantity epsilon 1 plus epsilon 2 plus epsilon 3 quantity squared, and then the second term is going to be a c1 minus a c2 over 2 times the term that's going to be epsilon 1 squared plus epsilon 2 squared plus epsilon 3 squared. Let's look at that term in a little bit more detail. Now, instead of using C1 and C2, we're going to use different coefficients now. Not sure why that keeps doing that. And the classic way to write this then is going to be with 1/2 lambda. Now, we've used lambda for eigenvalues of the strain tensor, but now this is going to be something different. This is going to be an elastic constant called a Lemay coefficient. And the second one is going to be, we're going to lump those two together as something called G, another of the Lemay constants. So it looks like this. U is equal to 1/2 lambda. Obviously lambda and C2 are the same, times epsilon 1 plus epsilon 2 plus epsilon 3 quantity squared. You may also recognize that as the trace of the strain tensor, plus G, and G is equal to C1 minus C2 over 2 times this quantity epsilon 1 squared plus epsilon 2 squared plus epsilon 3 squared. And those are known as the Lemay coefficients, and these are the elastic constants for an isotropic material. To be careful how I say that, maybe I should say these are elastic constants for a material that is isotropic. But I think you get the idea here. Now that G may look familiar. That's our shear modulus, or the modulus of rigidity that you would typically expect. The lambda can be written in terms of Poisson's ratio in the elastic modulus, or Young's modulus E. We're going to go through in a second part and go through all of that business to relate these elastic constants to one another. Before we do that, though, let's go through and kind of repeat this process that we did with this material science notation. We're going to repeat this process a little more efficiently for our tensor form of our Hooke's law. Well, from the tensor perspective, we can formulate a similar type of expression. What we're saying basically is that the stress tensor sigma is equal to something that would operate on the strain tensor times that strain tensor. Now the thing that operates on the strain tensor is going to be our elasticity tensor. Now I'm going to use the symbol C for our elasticity tensor. I may change that later to capital E for our elasticity tensor. But in an index-free type notation, something that turns a second-order tensor into another second-order tensor is a fourth-order tensor. So another way that we can write this then is that sigma ij in terms of components is equal to a fourth order tensor C ijkl times epsilon kl. Now Cijkl has 3 to the 4th components, and that means we have 81 components in our elasticity tensor. Now we already know that for the most general anisotropic material we only have 21 elastic constants. Only. That's still a lot of material testing to do. But if we have 81 components in a fourth order tensor, there must be some symmetries going on that we can figure out how to reduce this from 81 to at least 21. And we can do that. Alright, before we do our reduction in elastic constants, let's go ahead and show that our elasticity tensor is indeed a tensor. And we're going to do this by the use of our tensor transformation properties of the stress tensor. Okay, so at this point we already know now that stress is a second order tensor, so the components in the new coordinate system are equal to two transformation matrices times the stress components in the old coordinate system, where we've rotated about some point. So sigma ij is equal to AMI ANJ. That times CMN star, the new components, equals sigma ij AMI ANJ. Now we can replace our stress tensor with our elasticity tensor and our strain, and write this as Cijkl times AMI ANJ times an epsilon KL. And we can change the epsilon KL from its original coordinate system to its new coordinate system as well. with two additional transformation matrices APK and AQL times the new components epsilon PQ star. The star indicating that it's in the new system. Now this entire thing right here, since we have the relationship sigma mn star is equal to C, be a little bit careful here, C mn PQ star epsilon PQ star. This being the starred components being the elasticity tensor in its new coordinate system, then C mn PQ star is equal to AMI ANJ APK AQL times CIJKL. And then by the definition of fourth order tensor by transformation of components, then this is a fourth order tensor. Alright, well, let's exploit some of these symmetries to reduce our elastic constants. Alright, so let's start off with our general transformation from stress to strain. So C IJKL epsilon KL is equal to sigma IJ. But our stress tensor is symmetric, so that must also equal to sigma JI. And so what that says then is when I write CIJKL, I could just as easily write CJIKL. Likewise, sigma ij is equal to CIJKL is equal times epsilon KL, but that's also equal to CIJKL times epsilon LK. So then CIJKL is equal to CIJLK. Call that symmetry A, call this symmetry B. We also have something we can exploit in that because I take and I derive from a potential function my stresses with partial derivatives with respect to the strains. If I were to take second partial derivatives of this with respect to two different strains, epsilon ij and epsilon mn, then the order of differentiation is not important, so I could take second partial derivative of u with respect to epsilon mn first, and then with respect to epsilon ij. And that leads to a symmetry such that CIJKL is equal to CKL IJ. And taken together, A, B, and C makes the reduction from 81 terms that are unique down to 21 unique elastic constants. For a material that is isotropic. For a material that is the most general anisotropic material. Alright, so we've taken a look at material science notation in tensor notation. What we can do next is to see how this all works out to give a tensor form of Hooke's law. We can see how easy it is to invert Hooke's law in this case, which isn't really easy in the traditional way that we'd write 3D Hooke's law for isotropic materials. And we can find out exactly how our Lemay coefficients relate to our more familiar elastic constants E, G, and nu that we have for different isotropic materials that we would typically learn in our undergraduate mechanics materials class. Alright, so we'll take a break here and then we'll pick this back up in part B.